Hello, everyone. So today we're presenting our project analyzing lifestyle and demographic risk factors of diabetes using BRFSS data. So for our introduction, our project focuses on predicting diabetes using the BRFSS data set, which is the largest health survey in the US, and it includes demographics, lifestyle, behaviors, and medical history. And so our goal was to build machine learning models that classify people into diabetes, pre-diabetes, and no diabetes. So this data set was difficult because it's imbalanced, noisy, and includes hundreds of survey features. After cleaning, we ended up with around some samples and almost 200 features, and the target variables has three classes: diabetes, pre-diabetes, and no diabetes. And so we include demographic, lifestyle, and health-related variables, all of which have known associations with diabetes risk. The BRFSS dataset includes many placeholders. We replaced them and removed columns with too many missing values and encoded the categorical features. Because diabetes risk is influenced by behavioral and health factors, so we kept features with clinical relevance. And so after pre-processing, we obtained our final model-ready dataset. And now I'll pass it to Jyoti.
Hello, everyone. I'm talking about exploratory data analysis. So when we looked at the data distribution, the first thing that stood out was the class imbalance. Most people in the dataset do not have diabetes, and only a small fraction fall into diabetic and pre-diabetic groups. That imbalance matters because it makes the modeling task harder. In the first two plots, as you can see, the raw dataset had a huge amount of missing or invalid responses, almost half of the entries. After cleaning, the amount of valid data jumped to nearly 90%, which immediately made the dataset much more reliable. You can also see the patterns of missingness in this graph, which is really tightened up after cleaning. Missing the features became more stable and consistent. Then we explored how diabetes relates to demographics and lifestyle factors in these two graphs. The pattern were very clear. Diabetes is more common in older age groups, in people with lower income or education, and in those who report poorer overall health. These trends line up with what we expect medically. In the last plot, we are showing that people with diabetes show a higher burden of other issues like high disease, asthma, mental health challenges, higher BMI, and lower physical activity. So, this isn't just about blood sugar, it's tied to broader lifestyle and overall health. Overall, this part of analysis helped us to understand the structure of data, clean it properly, and identify the key patterns that explain who is most at risk. Now, Prem will talk about modeling.
In terms of the modeling phase of our project, we model diabetes as a three-class problem, which includes non-diabetic, pre-diabetic, and diabetic patients. We split the data set into an 80-20 train test split, which gave us about 360,000 training examples and 90,000 test examples. The main challenge, of course, was a heavy class imbalance. So on the training set, we performed eta-sign oversampling with class-weighted loss functions to boost the diabetic as well as the pre-diabetic classes. All the models optimize the weighted cross entropy or log loss, which penalizes overconfident mistakes. In terms of evaluation, we looked at six key metrics: accuracy, precision, recall, macro F1, ROC, AUC, and log loss. But our primary comparison metric was macro F1 because it weights the three classes equally, and it's more informative when the data is imbalanced. So in terms of baseline classifiers that we established four, which was multinomial logistic regression, naive Bayes, k-nearest neighbors, with two distance metrics, and decision trees. All of these were trained on the same data set, which was balanced using eta-sign as well as class-weighted, and evaluated on the 20% testing dataset. Naive Bayes gave us the weakest performance overall. It had a low accuracy as well as a low macro F1 and tended to collapse onto the majority non-diabetic class. Decision trees improved accuracy but still struggled on the minority classes and showed signs of overfitting. The two K&N variants highlighted the impact of the distance metric, which showed us that the Manhattan distance actually outperformed the Euclidean distance in both accuracy as well as macro F1, but still both of them were misclassifying various diabetic and pre-diabetic respondents. Logistic regression was the strongest baseline that we established. It had the highest macro F1 as well as a lower log loss while remaining simple and interpretable, so we treated it as the reference point when moving on to more advanced models. So in the next phase, in terms of advanced models, we moved to more expressive models such as random forests, XGBoost, and support vector machines using the linear kernel. Because of computational limits, we could not explore support vector machines using a radial basis function kernel or a nonlinear kernel. In terms of random forest and XGBoost, they achieved the highest overall accuracies, around 83%, and the lowest log loss, confirming that the tree ensembles captured a lot of structure in the data. XGBoost in particular gave the best macro precision among the advanced models and a very strong and a stronger, relatively stronger macro F1, so it struck a good balance between majority as well as minority performance. Linear SVM behaved slightly differently. It had a lower overall accuracy, but it achieved the highest recall and macro F1. So in other words, it sacrificed some correctness on the majority class in order to better detect diabetic and pre-diabetic cases. So when we put all this together, our main takeaway is that there's a trade-off. If the goal of our experiment is calibrated risk scoring as well as higher overall accuracy in the population, XGBoost and random forest will be the models of choice. However, if the goal is to be especially sensitive to diabetic and pre-diabetic individuals, the minority classes, then logistic regression and linear SVM trained with class weights and AdaSign are probably better choices. I'll now pass it on to Sanya to talk about the modeling visualizations.
Okay. Once the models were trained, we evaluated them using confusion matrices and ROC curves. The confusion matrices show that tree-based models like random forest and XGBoost classify the 4 diabetes categories much more accurately, while linear models and naive-based struggle with minority classes. The ROC curves back this up. Random forest, XGBoost, and decision trees consistently achieve higher AUCs, meaning they separate the classes more reliably. For KNN, we compared distance metrics and found that Manhattan distance forms tighter neighbor clusters and performs slightly better than Euclidean. Random forest's feature importance plot highlights the strongest predictors: general health, BMI, age, weight, physical activity, and income, which all align with known diabetes risk factors. Next, the decision tree importance shows a very similar pattern, and the logistic regression probability space plot helps visualize how the linear model draws its decision boundaries, especially between borderline and the diabetic groups. To understand model behavior more deeply, we used PCA to compare correct versus misclassified SVM points, which clearly shows where the classes overlap and where the model struggles. Sharp values from XGBoost add interpretability by showing how high or low feature values push predictions towards or away from diabetes. Finally, when we look across all metrics, accuracy, precision, recall, F1, and log loss, Random Forest and XGBoost clearly deliver the strongest overall performance. Logistic regression and SVM are stable and balanced, while KNN sits in the middle. Naive Bayes performs the weakest because its assumptions do not match with the data. Overall, the tree-based models stand out as the most reliable and interpretable options for this dataset. More static and interactive visualizations have been integrated into our project's README file and the results folder in the repository. Now over to Arnav for the conclusion.
In conclusion, we built an end-to-end machine learning pipeline that starts from raw CDC ASCII files and produces a cleaned, engineered dataset that models can reliably learn from. Through feature selection and cleaning, we cut hundreds of noisy variables down to a compact, clinically relevant set and dramatically increased the proportion of usable data. Our exploratory visualizations confirmed that diabetes risk clusters around well-known socioeconomic and metabolic patterns: higher BMI, older age, lower income and education, poor general health, and inactivity. Due to the severe class imbalance, especially the small pre-diabetes group, we had to use AdaSign oversampling and class-weighted losses. Even then, the borderline class remained the hardest to separate. Across models, logistic regression, Manhattan KNN, and the linear SVM gave the best macro F1, while random forest and XGBoost gave the best accuracy and ROC AUC. Together, these findings show how different model families trade interpretability, sensitivity, and raw predictive power. Our study contributes more than just model comparisons. It highlights real public health patterns at a population scale. The clustering of diabetes around old age, obesity, lower socioeconomic status, and limited exercise reinforces the multidimensional nature of metabolic risk. Importantly, even our best models struggle with prediabetes, showing that borderline individuals are not easily distinguishable and may require more targeted data collection or clinical markers. We also identified the variables that consistently drive predictions: general health, BMI, age, preventative care behaviors, and socioeconomic indicators, which align with both clinical practice and epidemiological literature. Beyond the results, the pipeline we built can be reused for future BRFSS cohorts and expanded with fairness analysis or cost-sensitive approaches. This makes our work not just a one-off project, but a framework that can support policy evaluation or assist researchers in understanding population-level diabetes risk.